Oh, okay. So when you're looking at the periodic table, trying to figure out, where did my stick go? These feel like, oh, there we go. If you're trying to figure out how many valence electrons you need to worry about within that, this periodic table is helpful, less helpful for you because it's kind of far away and it's a small font, but you can look at the Roman numeral. Okay. You can also look at the number directly in front. That one usually requires a little bit of interpretation when you're looking at the right-hand side or a P block, because we largely ignore the D block and there's 10 there. So if you subtract 10 from that number, you get your valence electrons. Does that make sense? What you will probably swiftly discover is you're not going to bother to use the periodic table to find the valence electrons because you will do it enough that you'll have them memorized. Okay? And if that sounds daunting to you, it shouldn't sound daunting to you because remember, we aren't looking at the entire periodic table. Really, that's all we care about. Okay? And even within that, we're largely just concerned about carbon, nitrogen, and oxygen, probably one of the halogens, probably chlorine or bromine. Okay? So it's really not that many elements that you need to memorize valence electrons on, and spending the time to memorize it probably isn't worth the effort. Doing practice with them is what's going to push that over the edge. Other questions?
So I think I remember you saying this, but I couldn't find it in the lectures when I was going back. But
Yep.
for Lewis structures, which elements can exceed octet?
Yeah. Okay, so what do we think? What elements can exceed octet? What's that? Oxygen cannot exceed its octet. Right? And if we cheat and look at our periodic table here, really none of them can. Officially, chlorine and bromine can. We'll never see them exceed octet as far as our class goes. But what elements can exceed octet? There was a hand. Somebody had an idea.
Is it like third row and beyond that can do it?
Third row and beyond. Why can they exceed octet?
It's really close to the d orbital, or they have a d orbital.
There it is. They have the d orbital. So when we're looking at expanding octet, it's expanding octet because you're moving beyond the s and p orbitals. S orbitals can hold how many electrons? 2. How many electrons can a p orbital hold? 2. How many p orbitals are there? 3, which means when we look at the p orbitals as a whole, how many electrons can they hold? 6. 2 plus 6 gets us our octet. When we're looking at Lewis theory was based off the simplest molecules first. So he started with effectively just the first 2 rows. And we look at the number of columns within our first 2 rows, how many columns do we get? 8, which is where we're looking at our octet rules. Okay? That octet rule builds out really, really nicely, and we don't really need to expand beyond that. There are certain circumstances where we can expand beyond that, and that's dealing with our d orbitals, which bring in more space for more electrons and more building outwards. Okay? But that requires that we add more space, and that adds a lot more complexity. That tends to involve d orbitals, and organic chemists can't count higher than 2, so we don't get to the d orbitals. Thank you for at least acknowledging that subtle humor. Okay? So we don't stress too much about expanded octets. It does show up, but it's going to show up primarily, as far as this class goes, phosphorus and sulfur. Okay? And in those scenarios, we'll see sulfur with an expanded octet when we look at sulfate, okay, or sulfuric acid. But really all we care about is that it's an acid. Did you know sulfuric acid was an acid? Okay, you don't care about the expanded octet. Okay, it's ultimately irrelevant. Phosphorus will show up in second semester again with sulfur as well, and we'll have some discussions about how that changes their reactivity depending on whether you expand the octet or not. Okay? Because believe it or not, you don't have to expand the octet. It comes down to different interpretations of what you're trying to deal with. Okay? And so we'll shift focus depending on what we want. That was a long-winded response to your question. Does that help?
Yeah, thanks.
Okay. Yes?
Explain how you find the charges. Like,
Yeah.
I was struggling with how to
Are any of those charged?
No,
How do you know?
doesn't show it.
Okay, so there's first step. We never imply charges, okay, which was a question that came up within the online homework, trying to draw things out, particularly in that first homework assignment. You have to draw exactly what is shown. And if you left off charges, it's wrong, because charges can't be implied. That must mean that they're always shown. Okay? Which addresses now your issue. What if I'm building out the structure? How do I know if there should be a charge or if there should not? There's multiple approaches to it. Where you're going to start with is calculating formal charge. Okay? The calculation requires math, simple math, but we don't like calculations, so most people will shift to a memorization approach. Okay? You should decide where your threshold is with it. My recommendation is you do a bunch of practice problems where you have to calculate it. You've now memorized it and it's stuck in your brain. If you just do an absolute attempt at memorization, you usually screw it up because you didn't spend the effort to actually hold that content. Okay? So if we go through and look at these don't show any charges. Was that correct? Well, how do we calculate a formal charge? Okay, well, one of the big changes, theoretically, that you're getting in organic is that you have to calculate formal charge for every single atom. And if we're looking at some of these molecules, these are really, really big. That can be time-consuming. So this is where memorizing patterns can help out with that. Okay, so let's pick any one of these. I'm going to go ahead and pick that carbon that we've now highlighted red, sort of highlighted red, and we want to calculate its formal charge. Okay, formal charge is looking at the balance of electrons around that molecule. So it needs to take into consideration how many electrons that atom brought into the picture and then what it has access to within that molecule. So our formal charge calculation, looking just at that carbon atom, I want to know how many valence electrons. Okay? It has nothing to do with the molecule. Carbon has how many valence electrons? 4. This would go back to that being able to quickly reference the periodic table, or if you've already internalized and memorized it. So carbon has 4. Okay? Now what I want to do is evaluate what's going on with the electrons around that carbon. Those electrons are represented in 2 ways. What are those 2 ways? Lines or dots. Okay? That's now how we would account for those electrons. The dots are relatively self-explanatory. A single dot represents a single electron. What does a line represent? 2 electrons. 2 electrons come together to make a bond. That's when we're allowed to use lines. Okay? So we can now go through and look at that carbon and say, well, how many electrons around it? Well, how many bonds do I see? It's a fun question. Okay, I don't know where 8 came from. I can see 7, okay, because the question was how many bonds, not how many electrons. So the bonds are the number of lines around it. Never mind, I see 8, for whoever said that. Bond, 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 bond. There are 4 bonds around that carbon. Minus 4. Okay? What about bond, bond, bond? Those blue ones. Those are connected to a different carbon. I don't care about those. I only care about the electrons around the carbon where I'm calculating the formal charge. Right? So those are irrelevant. The next thing I want to account for is where else my electrons could appear. My electrons could also appear in non-bonding electrons. Okay, how do I know I have non-bonding electrons? I have dots. Do I see any dots on that carbon? Nope, which means how many non-bonding electrons does it have? 0. Now I run the calculation, 4 minus 4 minus 0, and hopefully I get 0. Okay? So the formal charge on that carbon is indeed 0. Okay? What happens if we shift to oxygen in the lower right? Oxygen has how many valence electrons? 6 minus how many bonds? 2 bonds minus how many non-bonding electrons? 4. Anybody have a potential problem with how that's calculated? If you don't have a problem with it, I will tell you a problem with it. What is the unit on the number 6?
Electrons.
Electrons. What is the unit on the number 4? 4, I skipped one, sorry, was electrons. What's the unit on a number 2? Bonds. The unit changes. This is why when you talk about formal charge, if you talked about formal charge in Gen Chem, you see a slightly different formula, because that slightly different formula is super nitpicky on the unit being consistent. Why would that be important? Everything you do in Gen Chem is based off of units, so they're really trying to hammer home the importance of units. OChem, we don't really do any calculations. We don't care-ish about units. We just care about understanding with it. So we want to minimize the amount of mathematics, and we can shift that to now bonds instead of electrons. And as long as we're aware of our formula system, we're good. Make sense? Okay. This is now making the assumption you're looking at a completed Lewis structure. Okay? Which means if we think back to the Lewis structure building rules, we have to build out all of our structure and then associate a formal charge. All of these were completed structures where they theoretically were already neutral and done completely, so you could have assumed that they were all 0. Right? For the most part, we should assume that a structure given to you is drawn 100% correctly. Unless what? It's stated otherwise. Okay? You should assume that a structure you drew is drawn incorrectly until you prove otherwise. Does that make sense? Okay? That does kind of suck, but that's the process we have to work through. So you have to walk through and say, I'm always drawing this wrong until I can prove that it was drawn correctly. This means you have to understand all of the steps along the way to get there. Okay? Some of those steps get shortcutted once you've done enough and you've picked up common bonding patterns. Okay? The common bonding patterns did show up in the lecture recordings. So if I double back to that lecture, see if I can find it here real quickly. Sorry for the scroll. Whoop, there it went. Right there. That's our common bonding patterns, and I think if I start the slideshow, it's going to mess things up. No, it won't. Those are our common bonding patterns. Okay? So that if I'm looking at a neutral carbon, how many bonds do I expect to see? 4. Okay? What charge should the carbon be? And this is where we might get a little bit of shake on our rules, because if we look at our common bonding pattern, it shows 4 single lines, effectively on the faces of squares going off. Is that what I have here? No. So does that mean this bonding pattern system is flawed? Depends how you want to interpret it. This isn't saying you have 4 single bonds. It's saying you have 4 bonds. How do I know I have a bond? I have a line. How many lines are around that carbon? 4. I don't necessarily care where those 4 are located. As long as there are 4 there, that carbon is neutral. Make sense? Okay. So be careful with our bonding patterns and not over-memorizing things. And this becomes a very challenging thing to do or deal with, because what we're looking at here isn't all the possible bonding systems. Okay? They're simplifications and patterns that would allow us to build from them. Make sense? Okay. Let's try and quickly come up with an example here. Whoops. Okay. This is now being technically given to you. Okay, but this is something that, hey, we worked through and this is what we drew. Okay, so I'm not stating that this is correct. Okay. Is this correct? Brave. Why?
Because oxygen should have another bond or like electron in it, I think.
Okay. Just for giggles, let's throw another pair of electrons on it.
No,
Why should, you just told me to do that, and now you're saying don't do that.
because now it has 7.
And this becomes a careful thing that we have to deal with electrons. Okay, so 7, I think I understand where you're getting that 7 from. I think that counting is a poor way to count. Okay, what you're referencing is the number of electrons around the oxygen. How many electrons are around that oxygen? Okay, one interpretation is 7, and I apologize. Your Gen Chem instructor did you bad. Okay, they told you to count it wrong. You said 10, maybe because you heard me yell at him for saying 7. Fair. Okay. When we're talking about the electrons around the atom, we have to evaluate all of them. I see 1, 2, 3, 4. We should all be good on those 4. Now what happens is what's going on with these lines. What do those lines represent? 2 electrons. And they're bonds. What are bonds? Yes, 2 electrons. Keep going. Define a bond. There's our key word. It's the sharing of electrons between the atom, which means this single bond out here, which, sorry for the people at home, I'm not pointing to it, okay? You're looking at 2 electrons. Oxygen has access to those 2 electrons, okay? So it's 1, 2, 3, 4, lone pair, 5, 6, one bond, 7, 8, next bond, 9, 10, next bond. That means I don't have 7 electrons around it, I have 10. Am I allowed to have 10 electrons around it? Why not? And you should be able to answer this because you started the whole question cycle on this.
Because
It's okay.
electrons.
Octet.
Oh, octet, yeah.
Okay. We could exceed the octet if we're in the 3rd row. Oxygen's not in the 3rd row. You can't exceed the octet, which means this is now incorrect. So you zeroed in. I don't like the oxygen. That's ugly, man. You can't do that. Okay? I want oxygen to have 2 lone pairs. You're right. Oxygen should have 2 lone pairs and 2 bonds. When what? When it is neutral. Does oxygen have to be neutral? No. Okay? How would we know that it was not neutral? One thing, the hair standing on the back of your head, there's something wrong with it, which hopefully triggers your thought, how do I calculate formal charge? Okay, well, calculate the formal charge for oxygen. Oxygen has 6 valence electrons minus, I forgot how I set up the formula. The minus could go anywhere. So minus 2 for our non-bonding electrons, minus 3, because it's our bonds. You mean how we count changes a little bit? Yeah. Okay. What was our rule for formal charge? We didn't actually write it out. We just walked through it. So formal charge. Yes, valence. I can't write so fast. Slow down. Minus the bonds minus non-bonding electrons. How many valence electrons does oxygen have? 6. How many bonds does it have? 3 minus the non-bonding electrons. 2, which means its charge is. Okay. And I understand everybody saying 1. I would argue the number itself is pretty unimportant because when we go through and look at the charge, almost universally the charge on an atom will not exceed 1, be it -1 or +1. Why? You can't have more than negative or positive 1? It's the charge on iron. It's the charge on an oxygen atom. We can get these larger charges. Okay? When we're talking about organic chemistry, we're looking at building these molecules. And one of the things that's problematic with charge is it's inherently dangerous. It is very high energy, and we try to minimize that charge as much as we humanly can. Okay? How do we know charge is dangerous? You ever had a fork? What are you talking about? Yeah, of course they use a fork, right? You've seen an electrical outlet, right? You've been told to never stick it in there. Why? What's coming out of the wall? Charge. Okay? That's the electrons moving out of the wall. Charge is bad. We want to keep our charges relatively small, which means the majority of the time we'll either see +1 or -1. If we take a look at our summary chart here, what are the two charges that we show? +1 and -1, because those are the only ones that matter. So when we run this calculation, you saying 1, great, you can do math. I don't care about the math. I care about the magnitude. Is that positive or negative? That's positive. Okay, so I don't care that it's +1, I care that it's positive, which means I need to associate that formal charge now with that atom so that I know its potential reactivity. Make sense? So how do I associate that charge with it? Okay, there's a couple different answers that come out of it. The best one is putting a plus, or I would modify the best a little bit, but we put the plus as close as we can to the oxygen. What you may have been trained in Chem 130, if you took Chem 130 here, is you put brackets and you put the positive on the outside. You never bothered to assign the charge to an atom. Why not? We didn't care. We aren't reacting atoms. Organic chemistry, we react atoms. We need to know where the charge is located within the individual atoms. Okay, so we have to refine closer than that, and we have to specify it to the individual atom, which means we put the positive charge as close to that oxygen as humanly possible. Okay? The problem is when we run a chemical reaction, we're going to say we take this substance plus another substance, right? Which means I have another plus sign showing up. Is that plus associated with the carbon? No, that's the plus of additive of reactions, not a formal charge. So it might be nice that our notation notes that. How do we change the notation? It's silly. It's easy. Put a circle around it. Now I know that's not plus additive, that's plus charge. Now this plus without the circle around it, I know is plus additive, not plus charge. Simple language things, simple symbology that we use to help delineate and clarify that reactions. Okay? Why is it powerful to know the positive charge? Well, I said we could run a chemical reaction. Right? So I could do plus and I could put something here to say that something reacts with that. What do you think I could put in here that would react with this? I don't know. You don't need to know organic chemistry. I already told you the rule. What do we try to do with our charge? Minimize it. What do you think I could put in here? Something with what? Neutral charge, possible, but then when I run the chemical reaction, what happens to my charge? Stays positive. What would be the most likely thing to put in here?
Negative.
Something negative. If I find something negative, I now know it can potentially react. Neat. All we're trying to do is shuttle positives to negatives and arrange them in ways that make sense. Kind of, sort of? That's like 6 weeks. So good job. Okay? But first we have to understand our structures and our shapes and all that fun stuff. So we get this structure set up here. Okay? Is that the best structure? What defines best?
Subjective.
Best can be very subjective until you have a set of rules. Do we have a set of rules when we talk about Lewis structure to define best? This is going to come to how far did you watch your lecture videos? Yes, we do have rules for best because we have a secondary issue that will pop up, which is resonance, and we now have to be able to differentiate different structures, decide which one is better than another. Okay? On top of identifying best, what we typically discover is that best is not useful. What I want is what is useful, because that allows me to predict how chemistry reacts. For instance, when I go through and say I want to put in a negative thing to react with this, let's say N negative, okay, that negative thing is now going to react with this molecule. Where would I expect that negative to react? Why do I want it to react with the oxygen? To get rid of the positive charge. So let's push on it. This is pushing a lot further on it. Okay, so what we want to do is take those electrons and react them with that positive. Right? What would that look like? Okay, I've got my oxygen, right, with its electron. Okay, and I'm now sharing those electrons between the nitrogen, right? I didn't do anything to the triple bond or that carbon or that hydrogen, so those are there. We should probably delete that 23.
It'd be an extra bond? Or
Do you want to complain? You should complain.
I don't know what to complain about this time.
Oh, you should.
Don't you get rid of the non-bonding pair?
The non-bonding pair just falls off.
No, because it connects to the nitrogen.
I took this pair of electrons and I have shared them, because it's a chemical reaction. If I have shared them, what have I created? A bond. Okay? Deciding double, single, triple. I'm taking this pair of electrons and sharing them with the oxygen, which we said was positive, yeah? Okay, how many electrons am I sharing? 2, which means how many lines? 1 line, because a line represents 2 electrons, which means what kind of bond do I have here? A single bond, not a double bond. Okay? You could make the argument that I also want to share those back this way. What charge was the oxygen? Positive. Does it want to be positive? No. So what is it going to do with its electrons? Hold them. It doesn't want to get rid of them. Does it want to share those? No. It's like, no, I want to hold my electrons. I don't want to be positive. So it's going to hold those electrons. Those don't move. I would get this as a potential product. Why am I saying Peyton? Cool. Why am I saying Peyton should be complaining about this? If we rewind 10 minutes back, 20 minutes back, and we drew up that initial structure, what was your issue? You said you wanted another bond. Damn, that's exactly what we just did here, and that causes problems. That exceeds the octet. Ooh. That's a little strange. All right? So we have to be careful when we look at those charges, because those charges can fix themselves in different ways. Okay? That negative isn't going to go directly to that oxygen. It's actually going to go to other locations. Why those other locations? Does oxygen want to be positive? No. It cannot accept more electrons from an outside source. Because if it accepts more electrons from an outside source, what happens? Exceeds the octet, which it can't do. So that process doesn't work. If it can't get its electrons from somewhere outside the molecule, where must it get them? Where are their electrons inside the molecule? Closer than the carbon. The electrons in the bond between the oxygen and the carbon. So what we could do is say take those electrons and move them up to the oxygen. Okay? What happens? The oxygen has now gained a lone pair. We have one less bond now between the carbon and the oxygen. So there's our carbon, there's our hydrogen. What happened to the oxygen? Oxygen is neutral.
Not the carbon.
But now the carbon is positive. How do you know it's positive? I can think of at least 3 ways to tell me why it's positive. Okay. Octet is halfway there. One way, what did we say happened to those electrons? They went to the oxygen, which means the carbon lost electrons. If it lost electrons, it should become positive. You lose things, you become positive? Because it's negative. It's loss of debt. Yes, we become very positive when we lose debt. Okay? How else can we decide that that carbon is positive?
Valence electrons minus bond.
Formal charge. So 2 answers saying what the statement is and then how to do it. Carbon has how many valence electrons? 4. How many bonds? 3. How many non-bonding electrons? 0. 4 minus 3 minus 0 is positive. Okay, we don't care about the 1, but there's our positive. So our calculation does it. How else do we know? I think I heard someone say it. No? How else do we know it's positive? You mean that chart where we said you should memorize the common bonding patterns, because if we had those common bonding patterns, we could nail this down. If we go through and take a look at a carbon with 3 bonds, what's its charge? Positive. This carbon has 3 bonds. Why is it negative? It also has a lone pair, so we have to be wary of those lone pairs. So if we had the bonding patterns memorized, we also have the answer. That's at least 3 different ways that we could determine what the charge was on that atom. Okay? Why is it beneficial to look at this drawing? Nitrogen, it's N, so I'm thinking nitrogen. This negative thing can't share with the oxygen because it exceeds the octet. What if that negative shared with the carbon? You're saying yeah? What do you mean yeah?
It would make the carbon neutral and still allow the oxygen to be neutral.
We're not touching anything else. There's our carbon. There's our new bond between our I keep calling it nitrogen, our N, and our carbon. There's still our bond to our hydrogen. What happened to all of our charges? They're all neutralized. That negative N, should have that negative on there, is used to neutralize the positive carbon, and it neutralizes it in a way that we don't generate more charge. That's kind of cool. You've now come up with predictive power. Okay? Which then asks the question, we have 2 structures that we were looking at and thinking about when we're trying to predict the chemistry of this. Which of those 2 structures is correct? Dodgy. The left one is correct. Why is the left one correct?
Because it was easier to neutralize the carbon than it was the oxygen.
It was easier to predict the chemistry that came out of that. Okay, what I would argue is that that's a pretty darn useful thing to have. And to me, best would mean useful. Okay? What does spontaneous mean to you? If I said somebody in here was spontaneously combusting, what do you think is happening? Okay, out of nowhere, what does it mean to combust? Come on, flames burning up. Someone in here is spontaneously combusting. You all be like, whoa, where's the fire? Look at that explosion. Every single one of us is spontaneously combusting. What does spontaneous mean? In chemistry, what does spontaneous mean?
Without energy.
It's thermodynamically favorable. The products are lower in energy than the reactants. Why are we all spontaneously combusting? What are we producing? Sorry. We're not producing oxygen. Carbon dioxide. Where's the carbon dioxide coming from? The breakdown of glucose in our bodies into CO2. That's a spontaneous chemical reaction. Okay? Which means we spontaneously combust. This is why when we cease to live, what happens to our body? It continues to break down. Okay? The only reason it doesn't break down as we're walking around is we constantly supply energy to keep it maintained to prevent the overarching degradation. Okay? So chemistry uses language slightly differently, and this is where we have to be careful and decide what's going on with this best versus useful. Best is all in reference to Lewis structure. And when we draw out a Lewis structure, there's one overarching rule that is incredibly important that we must follow at all times. You already know it. Ideas?
Neutral.
Nope. Because we've got two drawings here, neither of them are neutral. So I would argue neutrality isn't a big deal. In a chemical reaction, we strive for neutrality, but we never obtain it. What's that? No, that's looking at where we would disperse our electrons. There it is. Octet. Right? When we talk about Lewis structure, we want all of our atoms to have an octet. So if we have the ability to arrange the electrons such that we have achieved octets on all of our atoms, that is more correct than another scenario. So when I go back and look at these two structures, do they both have octets? This means going through and counting all the electrons around each of the atoms. Let's take a look at oxygen. How many electrons around that oxygen? 1, 2, 3, 4, 5, 6, 7, 8. That's 8. That's an octet. How many electrons are on the carbon?
8.
1, 2, 3, 4, 5, 6, 7, 8. That's an octet. How many electrons are on the hydrogen? 2. That's not an octet. But hydrogen's in that first row. Our octet rule kind of falls apart. Sometimes you'll hear people reference it as a duet rule, which is just dumb. Just remember hydrogen sits at 2. Okay? It can't go more than 8 because it only has access to the s orbital. Okay? So if we look at that first drawing with our positive oxygen on it, those all have 8 electrons. How about the other one? Oxygen? 8. Carbon? 6. Does it have its octet? No. That structure, dang, I already blanked on the name. Okay? As you suggested, is phenomenal, is great, is useful. It allows us to predict the chemistry, but it is not considered best because it hasn't satisfied the octet. How important is that? When we talk through most of the stuff that we do within this semester and second semester, what we will look for most commonly is our useful resonance structures, because the useful ones allow us to predict something about reactivity. However, when we draw things out, we must always draw things as the best structure. This changes how we interpret mechanisms, how things move around. We started to do this already with our curved arrows. Okay? And it will also change when we look at draw Lewis structure for this molecule. Okay? If you have the option for resonance, you have to ensure that you draw the one that has the best octet. This question shows up on an old ACS exam. For the compound CHO positive, which of the following is the best Lewis structure? 70% nationally say it's this one. That would be the wrong one. And I would say, that's great. 70% of the people understand freaking chemistry. We shouldn't be penalizing that. The rule is best. Sometimes language wins and we have to deal with it. Okay? So make sure you're careful with best versus useful. This is going to muddy the hell out of our discussion on resonance. Okay? Because if we look at these two structures, if I were to ask, provide the resonance structures, at least early on in the semester, what we are asking you to do is to be aware of the best and useful. Unfortunately, what we teach you is that your resonance structures must all be of the same energy to count as resonance. Not really. Okay? So if you were asked on an exam to provide the Lewis structure, you need to be providing this one, and you wouldn't even approach looking at this one. The best is the only one you should be acknowledging here. Why does that one not count as a quote-unquote resonance? It doesn't satisfy the octet, which means when I compare those two structures, the best one is lower in energy, more stable, and therefore the only structure I should look at. The other one, while it is useful, doesn't satisfy the octet and is therefore higher in energy and therefore should not, quote unquote, count as resonance. That is an awful description to throw at you, but early on in the semester, that's kind of where we stick, which means I have to be very careful with asking questions on resonance to ensure that we get equal energy structures. Kind of, sort of? Okay. Who started that? That wasn't me. It's either Jazz or Peyton. You guys are the only one that started it. You think you can blame Jazz? Okay. Okay. We kind of getting a feel for what's going on with some of that? Okay. So if we go all the way back to here, I asked you to tell me what you noticed, whatever that was on Tuesday, right? Okay. And you all noticed a bunch of stuff that I didn't expect you to notice, okay? Which is good, okay? All I want you to start doing is looking for patterns, okay? But one of the things that you need to start doing when you look for patterns is also now ask me, be like, I see this pattern, is this a good thing? Okay? Sometimes it is a good thing, sometimes it's a bad thing, okay? One of the patterns that I would hope you would kind of see within this is that carbon has 4 bonds. Right? Which, if you had said that pattern, that's when I would have instantly drawn back something along the ones that we just looked at and been like, does it still have 4 bonds? Right? And you'd say, yes, because it has 4 lines. Mike, okay. And then I could go through and say, does that have 4 bonds? No. Does that make it an invalid structure? Ish. What's the ish?
It's not the best
It's
structure.
not stable. Like what it will be if it fulfilled the octet.
It hasn't satisfied its octet yet, so now the question becomes is what's going on with it. So we could look at some stability arguments behind this. Okay? Well, is it unstable because it's negative, or is it unstable because it's positive?
It's positive.
Why do you think it's positive? You mean because there wasn't an explicitly stated pair of electrons? Yes. Okay. Because as soon as we drop in that pair of electrons, now we go, oh, that's negative. Okay. What does that mean? Is it important to show our electrons? Yeah, that can show a really big difference. And those electrons are just a dot. Okay. They're you just pushing your pencil down. Okay. Which means I would suggest it's not just a simple pencil push. You actually make it a clear dot so that you understand there's a pair of electrons there. Because that's going to change that reactivity from a negative to a positive. If we bump it back to the pattern that we suggested, carbon should have 4 bonds. Does that carbon have 4 bonds? It has 4 groups of electrons, okay? And we can fix that since you said yes. We can switch it back to the positive one. It does not have 4 groups of electrons. Right? Does that make it invalid? No, it just means it's reactive. So I have to acknowledge some of these kind of differences within this reactivity. I can't just say carbon always has 4 bonds. Neutral carbon has 4 bonds. But a charged carbon could have a different bond pattern behind it. So I need to be aware of those kind of limitations behind how I'm thinking about and phrasing the patterns that I'm seeing. Does that make sense? Okay. What's the pattern that you see for oxygen?
2 lone pairs, 2 bonds. For neutral oxygen.
2 lone pairs, 2 bonds for a neutral oxygen. The oxygen did not have to be bonded to carbon. It could have been bonded to hydrogen, right, or carbon. And if we threw in water to it, it didn't even have to be bonded to carbon. Okay? Our carbons, looking at patterns, don't have to be bonded to other carbons. They could be bonded to hydrogens or other atoms. In this case, what we're looking at is oxygen. Okay? As we go through and look at these, though, if you were to draw all of those out as shown, would you be a little bit annoyed? Yeah? Why? You very aggressively agreed with me that you would be annoyed, but you don't know why you're annoyed.
It'd be a pain in the ass.
Why?
Because it's a lot to draw.
Okay, how could I simplify it? Okay? Instead of drawing C's for all of my carbons, I could assume those were points. Okay? Makes the most sense with this one. I could do it with the first one, but that one's a little bit silly, because what's that? Well, actually, it's not that bad. I could draw that. Right? And if I made you wait as I drew all of those out, would that also take a bunch of time and you might be a little bit annoyed with me? Yeah. What else could I do? CH4, that's an interesting statement. Okay, now you're taking it all the way to a formula. Okay, and for CH4, that's not a big deal. Okay, but I would argue for these two, that would be problematic. And the one I erased, but I already erased it. Why would it be problematic there? How many carbons do each of those have? 4. How many hydrogens? 10, which means the formula would be C4H10. I'd be saying those are identical. Are they identical? No. What's different about them? There's a carbon bonded in a different spot. Does that cause a change in reactivity? Well, think about it. If my arm was not connected here, but was connected off the middle of my forehead, would you respond differently to me? Does it change the reactivity? Yes. Okay? Because it changes the reactivity, using a formula to represent that compound or group of compounds becomes problematic, because my reactivity could be vastly different. Okay? Which all goes to say, all that stuff you did in Gen Chem where you looked at chemical formulas is utter nonsense, and we don't want to look at chemical formulas anymore because the chemical formulas don't hold enough information. And we would rather look at structures. But when we go through and draw structures, that takes more time, that takes more effort to build out, and that becomes problematic, which is why we don't do a whole lot of that in Gen Chem, and that's also why when we look at the periodic table that we use in OChem, we don't use the whole flippin' thing, we only use like 10 elements, so that we don't have to work as hard to draw all of those structures out. Okay? We also go through and make other simplifications. We dropped the carbon and assumed just a point, an intersection of lines. Actually, not even an intersection of lines, just a point is a carbon. Okay? But even if I made that simplification, that's still drawing a lot of other stuff, right? Could I make another simplification?
Since, like lone pairs have to be drawn out, you can imply hydrogens are there because it's no lone pairs, so it has to be octet.
If we're talking about it, someone used the name hydrocarbons on Tuesday. Almost everything we've got has hydrogen and carbon in it. We can imply the carbon as just points within our drawings, and we can imply the hydrogens. Well, how many hydrogens can I imply? One per bond. Okay, there's an interesting theory. So let's go ahead and take a look at that first one. 1 per bond. Have I implied my hydrogens? Well, now aren't these all hydrogens? Well, just 1 per bond. Each of those lines ends on a hydrogen. But if each of those lines ends on a hydrogen, what else do they end in? What does a line start with? Fair point. It starts with a point. What did we say points were? Carbons. So if I do this and just say, well, the hydrogens are out there, this drawing is now confusing. Am I implying hydrogens are on that perimeter, or am I implying carbons? According to my rule that points are carbons, I'm implying carbons. I no longer have CH4, I have C5. We'll ignore the hydrogens for the moment. Okay, so how do I imply the hydrogens? For this first one, I think it's a bit silly to draw, but we're going to draw it. If I can draw it. There it is. Everybody see that? What is it? It's a dot. Okay? That dot, because what we said, carbons were just points, there's our carbon. How do I know it has 4 hydrogens? There's no charge, and since I know the common bonding pattern for carbon needs 4 bonds, I had to figure out the fingers, there must be 4 hydrogens around that to satisfy it. Okay? That would be obnoxious to draw, which is why typically when we talk about methane, we would draw it out as CH4, as my pencil doesn't work, or we would draw it as we drew up there, or with the cross and the carbons. What happens when we move to the next one with the 2 carbons? 2 dots? The dots are connected to each other, so it's not even 2 dots anymore, it's just one line. That now represents those 2 carbons. You're like, this is silly to look at it that way. But it helps simplify when we move to larger structures. All of these structures are relatively simple, right? But they start to get some of this information in here. If we move to the next set, what do we get? Well, we get line, line. How many dots were in that? 3. Can you see 3 dots in that? No. Okay? So that becomes difficult. Okay? That's still technically trying to represent that, but our perspective on it is challenging. Okay? So if I asked you to draw what was on the screen of my iPad, you'd be like, okay, yeah, I can draw what's on the screen of the iPad. Can you really? Can you draw? What's on it? Well, you need to turn so I can see. Exactly. When we look at our drawings within OChem, we have to be very selective about what angle we're looking at the molecule, because depending on the angle that we represent, it can make things obvious or impossible to understand. So for this particular one, what we should be drawing is not just a straight line, because that's very confusing. What I should do is put a bend in it. Why else should I drop a bend in it? It allows me to see the point, which is valid. Why else should I drop a bend in it? What are we trying to represent with our drawings?
The structures.
Molecule.
A 3-dimensional physical object that we can't touch or see or any of that, but it's representing an actual physical object in space. Okay? Which means I want to throw that bend on it, because when I look at this molecule, is it just a straight chain molecule? No. How do I know that? I would argue there's 2 ways. Experiment. We tested an experiment. We noticed it's not straight. It was bent. Why is it bent?
The hydrogens need to be bonded.
Because of the carbons and the hydrogens. I'll accept that. Okay. Where did bond angles come from? How do I know what that bond? What is that bond angle supposed to be? It's not 90 degrees. If we look at the Lewis structure, it looks like it should be 90. It's not 90 degrees. If we look at that Lewis structure, let's just pick one of those carbon atoms, okay, and we'll look at that angle in there. Okay, it looks like it's drawn 90 degrees because that's an artifact of how Lewis designed things. He removed information so he could simplify his drawings. Once we've got the drawing, we now have to interpret the 3-dimensional reality of it. What do each of those lines represent? What's a bond? Electrons. What happens when electrons get near other electrons? They repel away. Why is that problematic? What are each of those groups of electrons trying to do? Get away from each other as far as humanly possible. They can't go all the way away because they're all bonded to that central carbon. So what's as far away as humanly possible? It has a theory. There's a name describing this theory.
Vesper.
It's Vesper. Valence shell, the outer electrons, pair repulsion theory, electron pair repulsion theory. It's all of those electrons repelling away from each other, and it generates a particular shape. When we have 4 groups of electrons, or 4 regions of electrons, they repel away from each other to form the tetrahedral shape. And if we now look to the bond angle within the tetrahedral shape, that comes out to be 109.5. Why do I want to show that bend? What I'm trying to do is not only allow me to visualize that I have that other carbon in there, but I'm also trying to represent the actual bond angles within the molecule. Why does that matter? Seeing my arm bend this way, you're probably like, oh, that's cool. But if I bent it the other way, you might still think it's cool. I probably wouldn't. Okay? That makes a big difference in how we interpret our chemical reactivity and all of those pieces. So we need to be aware of that. So that knowledge gets built into our structures. Kind of, sort of? Okay? If we took a look at those top two structures, right? Do they look different? Yeah. Okay? One abbreviation, we got 3 carbons. 1, 2, 3, right? What is this one going to look like? 1, 2, 3, right? Are those different? There is no up, there is no down, there is no left, there is no right. What does that mean? They're identical. All you have to do is take one molecule and rotate it. Okay? The example I typically give, and you'll get it a lot throughout the semester, what's my name? Thank you. What's it now? Careful. Theoretically, it's the same. Okay? But how we would visualize and see that object may change, which means you, as an organic chemist, need to be able to look at those two and recognize, oh, it's just a simple twist to the paper. They're identical. Okay? That's challenging to pick up. It's extra challenging to pick up if we draw it the way Lewis designed things. Okay? So our simplifications can help us simplify our drawings, allowing us to manipulate it. Make sense? Yeah? Ish? Okay? And if you struggle with it, one of the other things that you could potentially do, you could take these two drawings and you could build a model kit. You take 3 carbons and you shape it like this, so you're looking at it, right? There you go, 3 carbons. There's the carbon at the end of my pointer finger, carbon in the middle, carbon where my thumb is, right? That looks just like that one, except not purple. Doesn't it look the same? Yeah.
Is this, I've seen that those spider type of models, is this what this is, that those are based off of, the lines and then the angles and that sort of thing? Is it giant to like tetra?
The only spider models that I'm aware of are looking at spider diagrams for chemical reactions, so I can't answer whether that's true or not, because that's not this. That's summarizing different things. Okay? Kind of, sort of? You feeling spicy? Like you got it? It's easy? A little bit of practice, hopefully it'll build and you'll be able to nail that down. What happens when we move over to the other side? And by other side, that was a stupid way to phrase that question. We bring in those 2 molecules. Why are those 2 molecules slightly different? There's an oxygen. So if we were to go through and do this, could we go, there's carbon 1, carbon 2. We could emphasize those with dots if we really chose to. We're only doing that for the sake of emphasis here. And then it's connected to an oxygen. Can I imply the oxygen as a point? No, why not? I already implied points as carbons, which means I have to explicitly state oxygens, which means this representation, when we go through and look at it, come on, pencil, or maybe I can do this one. Maybe I like this better. Where'd it go? There it is. That part right there, everybody see that? That's not a point. The point is the oxygen. Our line ends in the oxygen. So this is still 2 carbons, and that bond now ends in that oxygen. Does that make sense? Okay. What else is that oxygen connected to? Hydrogen. Can I imply the hydrogen? It's going to look kind of weird now. I'm trying to decide what it is. Well, but we won't. We could pause on that and be like, well, maybe we can. Can I imply the lone pairs? right? Which now introduces an issue. What can I imply, what can I not? Right? Well, we shouldn't imply the lone pairs. If we're going to imply the hydrogen, then we draw this. Why does that now look weird? What's that?
Because they're dots with the carbons.
Fair point. I never processed that. When we're talking about the dots should either begin or end a line. So if we see a dot floating, that's not carbon anymore. That's a lone pair. That's a non-bonding pair or a non-bonding electron. So dots just chilling out on their own. It's not just a solution of methane. It's electrons associated with whatever atom is closest to it. Good point. Does that make sense? Anthony, I think you said it. How many lone pairs should oxygen have?
For a neutral one?
Yeah,
2 lone pairs.
2. How many bonds?
2.
What do you see?
1 bond and 2 lone pairs.
Oh, that's because there's an implied one. Well, that starts to get dodgy. Okay, and it starts to become a little confusing. Okay, which means ultimately when we imply our hydrogens, we can only imply them on carbon. We don't imply them on other atoms. Why? Because we decided it's how we draw. Right? When you draw a stick figure, you usually have the circle on top of the head, right? You got the circle, the body, the arms. Okay? That's our implication behind how we draw that. We just accept it. So there's certain things that we just have to accept within our drawing patterns, and this is one of them. Okay, which means I cannot imply that hydrogen. I must specify it, so I will show that line out to my hydrogen. Now it's easier for me to see that my oxygen has its full octet. This allows me to see the electrons. The electrons are useful because the electrons do the chemical reactions. So everything we do is about moving where our electrons go, so that's awesome. Okay? But if I had a molecule with a bunch of heteroatoms, so not carbons, we're looking at oxygen, nitrogen, and our halogens, what have we been drawing a lot of? Dots. Lots and lots of non-bonding electron dots. Okay? And that gets tedious very, very fast. So while you might be like, but it's useful to have them, an advanced organic chemist is like, I don't want to flip and draw all these stupid things because it's a pain for me to deal with. So they say, well, tough people learning organic chemistry, guess what we're going to do? We will imply non-bonding electrons to heteroatoms. How many non-bonding electrons am I implying by drawing this? 4. I just erased them. How do I know it's 4 and not 2?
Because we want oxygen to be neutral.
I accept. I didn't like that answer, but I accept. We want our oxygen to be neutral. So you've memorized the common bonding pattern for oxygen, and for oxygen to be neutral, because we can't imply the charge, because we've implied hydrogens. Okay? For oxygen to be neutral, it has to have 2 non-bonding pairs, which would get me 4 electrons in the 2 bonds. How else would I know that I need to have 2 non-bonding pairs? The octet rule. That was the answer I wanted, but you're totally right. Okay? Octet rule. Oxygen needs to have 8 electrons around it. It currently has, depending on how you want to count it, 4 electrons around it. There are another 4 electrons as non-bonding pairs of electrons. The implication of non-bonding pairs of electrons is a very dangerous thing to do. So much so, I will strive my best to not imply them, which is why when we look at these drawings, you see the non-bonding pairs. Okay? Which is why when you do smart work homework assignments and they say show the non-bonding pairs, you have to go through that extra effort to go through and include them. And the reason we want to include them is that's where the chemistry is located. That's where our reactivity is. And so we want to include them so that we can see that chemistry. Then why do advanced chemists get rid of the lone pairs? Because we don't always want to see it. Sometimes we do. Sometimes we don't. And since it's a sometimes scenario, it's not good to throw that at you. We should make it a blanket statement and just say, always show them. As you get more experienced, that's when you can start to drop them off. Okay? Make sense? We addressed one last part of this as well. We can never imply formal charge. So if I looked at something like that with that oxygen, this floats in this really strange gray area. Did I imply hydrogen? I know I'm not supposed to. Right? Did I imply 3 lone pairs? If I did imply 3 lone pairs, shouldn't it be charged? Okay? It becomes very confusing to assess this, which is why you never leave off formal charge. It always has to appear. Right? In this particular drawing where we've implied all those electrons, that becomes difficult to assess the charge on the oxygen because I don't have all those electrons present. But if I had memorized that oxygen needs its octet, I would say it has 2 electrons, 2, 4, 6, 8. Now that I have my drawings included, I could go back through and say that I needed that negative charge to match the bonding patterns. We excited? Yes?
So, do you want us to like draw the bond of hydrogen, or just do those 2 lone pairs and then add the negative sign?
When it's negatively charged, should you be drawing the bond to hydrogen? No, because it's negatively charged. If it is a neutral oxygen, I need another bond. Okay? Does that bond have to be to hydrogen? No, it can be to anything, okay, which is why we typically need to specify it. Okay? We don't want to imply it because that implication could have been a carbon. So that's why we have to be extra explicit in identifying that hydrogen.
The formal charge, you have a question that's like, what's the formal charge for oxygen in this structure? Or
Yes.
would you say what's the formal charge of this structure?
We would never ask for the structure. Okay? For the structure is now Gen Chem. We don't care about that anymore. We're advanced. We need to know where the charge is on an atom. So you would look at the molecule and you'd have to say, what is the formal charge on a specific atom? So if you looked at a structure where there were multiple places for charges, I would have to specify which atom. Kind of, sort of? Yes?
So is that the correct way to draw that, or?
And of course, correct is a dodgy statement. This is a correct way to draw this molecule. This is also a correct way to draw this molecule. This is also a correct way to draw that molecule. This is also a correct way to draw that molecule. This is also a correct way to draw that molecule. Why would you choose one of those drawings over any other?
It's more useful.
It depends on what you're using it for. Okay? So if I wanted to know what all the atoms were, this one makes sense. If I want to know its three-dimensional representation with all of the atoms, I'd need to be drawing something more like this bottom one. If I just want to draw the molecule because I want to see it as a solvent and just say it's just chilling around and I don't want to write out the name of the compound because I'm lazy, that top one works. Okay? Is that a happy answer? Yeah, that's a happy, I would argue that's a mean, awful answer. Okay? It all depends on the circumstances under which you're in. Okay? And if you're like, well, that's not true in real life, really, you just walk up and kiss and hug everybody in your life. Like, no, depends on the circumstances you're in. Right? You may even give me a hug and you're like, I would never give you a hug. I saved your life. Yep. You're probably like, thank you for saving my life. Yep, that changes the circumstances. Okay? Lots of things can change how we interpret things, so unfortunately we have to shift and kind of move with those balances. That's one of the reasons why I try to spend so much time looking at Lewis structure and how those things manipulate and change, because as we move through, we will add information or remove information depending on what we want to do. And there are plenty of scenarios where we'll achieve something in second semester where we're looking at it being like, oh, this reaction does this cool thing. And someone will ask, why does it do that cool thing? I'll be like, you remember that one way that we could look at a molecule back in OChem 1, that Newman projection thing that you really hated and you didn't like? Well, since you asked why, let's take a look at that chemical reaction, but let's look at it from that perspective. convert the drawing out into that perspective, ta-da, that's why. Because the change in the perspective provides us that answer choice or that validity that allows us to navigate it. So we have to be aware of all of those pieces. Do we need to do it all the time? No. Okay? That's what makes OChem so challenging and arguably fun. It sucks to be tested on. Not going to lie. Okay? I did kind of want to get to resonance. I mean, that clock says I've got 45 seconds. Okay? I do want to call out some other things, so I don't think I'm going to get to resonance. Smart Work 5, we talked about all these different things that you have to watch out for. It's very detail-oriented. Smart Work, our online homework, insists on you being perfect on how you draw things out. Okay? So there's a variety of things that you will have to track. You need to make sure your bonds connect to atoms. If I want to draw methane, okay, in class, we draw up here. I could draw a line, right? Line, hydrogen, hydrogen, and you'd be like, that's methane. What Smart Work sees is line and line. You never connected the atoms. Okay? So you have to be very explicit by connecting atoms through your drawings. Okay? That's the three-dimensional representation. This is one of the problems where online homework systems struggle with. The best way to do it is draw your answer. There's a little 2D like button in the upper left-hand corner. Click that. Your image will move around and do weird things. As long as it's all connected, you'll see one structure still. If it's not connected, you will now see two separate pieces. Okay? So it can help you kind of troubleshoot some of that. The orientation of bonds and shape, this is dealing with Vesper, does matter in certain scenarios, sometimes not. It again depends on the system. We'll encounter those as they pop up. Okay? Two common ones that would appear if we're looking at Vesper. That is a valid representation for a tetrahedral carbon, a carbon connected to four other things. That works. This does not work. Okay? What does the wedge mean? It's at front. It's coming out at you. What does the dash mean? It's going away. What does the solid line mean? It's in the plane of the paper. It's not a directionality. It's just the plane of the paper. There is no way you can orient a molecule to make this drawing on the right exist. It's physically impossible. Which means if you enter this into Smart Work, it can't grade it and it gives you a 0 for it. Okay? If you draw things like this and try to interpret the structure from this, you will also get this answer wrong when it comes to even multiple choice exams. So we have to be very careful about how we represent and draw things. Non-bonding electrons become important. Formal charges are important. Because it showed up in the background information, arrows, double versus single, arrows always show the motion of electrons. Most of what we deal with is moving pairs of electrons. How do we know we move a pair of electrons? Our arrow has two heads. That's a pair of electrons. If our arrow only has one head, we have moved one electron. So you have to be careful to note what arrows you're using. Digital systems struggle with making arrows look nice with all those bond angles. Hand drawing, it looks a whole lot nicer, but you do have to be aware of that. Unfortunately, I do need to stop. I mean, I think it's unfortunate, but